Sorry, I got interrupted there. So, you're going to be able to spot this tough one every time when you see, where was the tough one? Oh, right there. I think I did that already though. When you see a third cubed, or a cube that, something that can't really be factored. And that's going to be the secret. So when you can spot that, they're talking about a tough one. So I'm just going to write what you have to do. Obviously, you can't take a cube root of this, and there's no way you can multiply by a conjugate. Although technically, I bet you could multiply by the conjugate. I wonder if they even thought of that. We've tried both ways. I bet you could multiply by the conjugate. But it's clear that they want you to do this. They want you to make a u cubed equal to x plus 8. Okay. And didn't I already do this? Yeah, I guess I was just finishing up when the phone call came. So that's what they want you to do. And u cubed. And as a result, the x is going to be equal to u cubed minus 8. So you got to write these two terms. And you also have to realize that when u cubed is equal to x minus 8, and when x is reaching 0, that means u cubed is equal to 8. So really we're looking for u approaching 2, because u is equal to 2 here. So when you do transfer it like this, you have to figure out what the limit becomes. So what we're really looking for now is the limit of u as it approaches 2. And you're replacing that top term with u cubed to the cube root. And then you're replacing this x with the thing you learned right here. And that way we can take the cube root up top. And you might say, well, I'm still stuck with my problem at the bottom, because if I make u 2, it still becomes 0 down here. Yeah, and that's when you got to remember your factoring, your difference of cubes. So you get u minus 2, and it's u squared minus 2u, plus 2u plus 4. And right away you can see these are canceled. So now you got this over u squared plus 2u plus 4. And thus when u becomes 2, not 0, you get 4 plus 4 plus 4, which is 1 over 12, equals positive 1 over 12. And so that's really the answer to this. When this whole thing will approach 1 over 12 and never quite reach it. For this, you'll have a hole in the graph for this situation. Now my question is, could I have instead converted that to a cube root of x plus 3? Oh yeah, here's the problem with the cube root. You can't do conjugate, and that's why you spot it. You can't do conjugate because when you multiply a cube root times itself, it doesn't become the innard. That only works with a square root times itself. You'd be left with x plus 8 2/3 root. Or if you want me to put it in a better way, it would look like this. X plus 8 squared and rooted, which is still not solvable. But I think it might be possible if you multiply it 3 times to come up with a thing that works, but then you're looking at a nightmare factor when it's a lot easier to use the imaginary number of cubed. But I think you could do a triple conjugate and get rid of it. And then you just end up with a huge mess at the bottom, though. Let's look at 9, and I'm just going to spot them for you, and you can do them. You don't need me to do all of these. Okay, this one is clearly going to be remembering that the top is a difference of squares, and the bottom is a difference. It's not a difference, but it's still a cube. It's called added cubes, or I forget what the term is, but they're still cubes, because 4 times 4, which makes 16, times 4 is 64. So you get x plus 4, and it's x squared minus, I think it's minus 4x plus 16. So this is the squared, this is the two opposite each other, and you use the same term, and this is going to be the same as that. And if you're uncertain, you can multiply it out and find out. Maybe I got it wrong, but it doesn't matter. My point is, it's clear here what's going on. And when you're left with this, when you make x approach 4, I think it is right here, it works out fine. Because this becomes 16 minus 16 plus 16. So it becomes 16 down here. And up top, it becomes 4 minus 4 is 0. So it's really approaching 0. But it's solvable now. Okay, so that's that one. This one here is also a difference of squares, and it's clear at the bottom. They're never going to give you something where it can't be solved, really. It's not the point of math. And it's clear that down below I'm going to have a factor that's like that. So it's going to be minus 2 minus 3, I think. Let's see if that works. It's not x plus 4 down there, so I'm surprised they're giving it to me. Down below it's x minus 2, x minus 3, oddly enough. And, oh, maybe, is this a difference of squares again? Nope. Now, if this was x to the 4, that would work out, because it would be x squared, x minus 4. And then the second one here would become x plus 2, x minus 2, and this cancels out. So maybe that's what they were thinking of. As it is, maybe it can just be resolved without it. It's x squared, so it's not that. So if I look at the bottom, 4 here, 16 minus 20 plus 6 can't work. And oddly enough, I think they meant x to the 4 minus 16. Well, we could try. It's clear they wanted a factor. The problem is the bottom factor doesn't have a 4 in it. It has an x minus 2, x minus 3. That's there. And the up top would only have this in it if this said x to the 4 minus 16. Then that would work. So I don't know what they're going for here, because up top you end up with x plus 4, x minus 4, and none of this cancels out. There's no way to make it that it cancels out. Very odd question. Maybe they made a mistake, or maybe I'm just not seeing it. You'll have to consult the book. If they say the answer I said, then they've written it down wrong. This one is pretty easy. And you can overthink things, but if you take x out of the top, you're left with x plus 1 over x plus 1, and they cancel. So as x approaches minus 1, this whole thing becomes minus 1. D is clearly a conjugate, so multiply it by this. Oops. Let's go back. It's clearly a conjugate, so you just take this and you multiply top and bottom by its conjugate, which always has a plus sign. So up top you're going to be left with x plus 1, and at the bottom you're going to be left with x plus 1 minus 1. So you're going to be left with x up top, and the bottom you're just going to be left with x plus 1, and these are going to cancel out. And then you can put 0 in for x, and you're left with 1 over 2. Let's see what else we got there. This is a difference of squares, and you'll see that when you resolve it, you're going to be left with h at one of them. One of them is going to be x plus h minus h, so it's just going to be x, and it's going to cancel out. So it's just going to be x plus h minus x, rather. And so the x is going to cancel out, and then the h's are going to cancel out. Pretty much. And you're going to be left with x plus h plus x at the top. So it's 2x. So as h approaches 0, you're left with 2x. Will be the answer. Oh, I think maybe that one's worth doing because there's no value we can put in. So clearly in this one, they're trying to reach as h approaches 0. And this one's relevant because that will be a lot of our instantaneous, that'll be a lot of our derivatives. So it's clear that why they're making you practice this. So the secret to this one is to notice that this is a difference of two squares. And this two squares are x plus h, and just treat that like, like an x, plus this, plus x, times x plus h in brackets. minus this. See, here's the square root, and here's the square root. And it's all divided by h. And then, obviously, this part cancels out. So you're left with x plus h minus x becomes just h. So you're left with h times this mess divided by this, so they cancel out. So up top, you're left with x plus h plus x. So as h approaches 0, this just becomes x plus x, which is 2x. So the answer to this, what is the limit for this one? Or did I do the right one? Sorry, for this one, it's 2x. Oh, no, yeah, for this one. And I got a funny, it looks like y there. Yeah, this is 2x. And then this one looks complicated and you can really freak out easily. But it's pretty clear that when you're given fractions, if x is 1 at the bottom, it all becomes 0, so that doesn't work. But it's pretty clear here that you're going to be cross-multiplying to just subtract this fraction. And that you'll see why in a second. So how do you cross-multiply? This whole thing multiplies this top. This whole thing multiplies this top. And then this will stay as the denominator because they multiply each other. So here's how you cross-multiply. It helps when you keep things in brackets. Whoops. So that will cross-multiply that denominator. That will cross-multiply the 2. So it helps again if you put it in brackets. And it's going to be minus 2 times all that. And then the bottom is going to be one long denominator, which is this. It helps if you put it in brackets again, times that. So I'll just use the ones that I put in brackets. It's a lot easier for that one and that one. And then don't forget, I'll just move this over, that it's still all being multiplied by this. So again, if you look at this and just put this all in one big bracket, that helps. And it's for the limit as x approaches 1. Well, right away, if we resolve this up top, we get 3x plus 5 minus 2x minus 6. So what's 3x minus 2x? It's 1x. What's plus 5 minus 6? Minus 1. So this is what we're left up top. And I'll just put it all back. That's all we're left with up top. So it's clear that, you might say it doesn't divide with any of the bottom. No, but it divides over there, which is multiplying this whole thing. So it's just 1 up top. And we're just left with 1 over these fractions. And then you just plug in 1 in here. And remember, they're multiplying each other. And you get 1 over 4 times 8. And you get 1 over 32. And that's the limit of this. And so you can see you're using all sorts of techniques to figure out the limit when you can't just substitute. And that's what they want you to do. Okay, by using one-sided limit, I probably won't do this because I hate absolute value. I don't see the point in this. And I'm going to guesstimate here. And I might be wrong. But you can just plug these in the Desmos. It's the best way to see if you're right or wrong. But every time this cancels out, from the left side it's going to reach the minus 1, and from the right side it's going to reach 1. That's all there is to it. Same with this. If you look at the top, it's x minus 2, x minus 1, yeah, x minus 2, x plus 1. And you can see whenever it's over the opposite like this, on the right side it's going to approach this whole thing here is going to be a positive 1, and on the left side it's going to be a negative 1, which means the whole thing from the right side is positive 1 time and negative another. So again, there's not going to be a limit as you approach, and the limits will be opposite. We're approaching the right side will be this, approaching the left side will be minus 1, and it happens over and over again. Here it is here. So there's no point for me doing over it again, especially since I know on the right side of these things it always approaches plus 1, and on the left side it's minus 1. And then over here you might say it doesn't exist here, except that this is x plus 2 times x plus 2 times x plus 2. So again, on the right side these will become positive, and on the left side they will become negative, which means I guess what you can do is figure out what the actual number is when it approaches it. So you can put 5 over 2, but I don't see the point. So this one will be plus 1 minus 1, and this one will be, when x is 2, we get a 3 over here, so it's going to be plus 3 and minus 3 from left and right. But what's the point? They're not the same limit, so what's why they're doing it? This one, because we have the two extra x plus 2's and x plus 2's, so when this becomes minus 1 or plus 1, we're talking about 0. So its limit will be 0. There we go. So this one will actually be relevant. It will actually reach a 0 from left and right. So that one does have a limit. Maybe that's why they're doing it. And this one, when these flip-flop between plus 1 and minus 1, when it goes from the right side, it's going to be, what's 2? 7 over 2. And when it approaches from the left side, it's going to be negative 7 over 2. What's the point? No limit. No limit. No limit. That one's a limit because the top numerator becomes 0. It doesn't matter what these two become. So my bad. Do them if you want. I don't care. This is just a measurement, and he wants you to show that we have a linear equation. So Desmos has this really nice thing, and I think that's maybe what they're trying to get you to practice, that you can put in a table into Desmos. You can even copy it from Excel. You make this nice table, and you determine on this formula which is the x value. So he's discovered that the volume of the gas at constant pressure increases linear with the temperature. So the volume of gas changes, and the volume was measured in liters, and the temperature was measured in degrees. So you can see that your x values is going to be your temperature in degrees Celsius, and you get minus 40, minus 20, 0, 20, 40, 60, 80. And then you get these numbers on the right that match it. I'm not going to do them over and over again. And you're going to show that it's linear. But to do this, you're going to take first differences and second differences. And if they're first differences, it's linear. If they're second differences, they're parabola. If it's third differences, they're cubic. If there's four differences, it's quartic. That's how it works. So you're going to see that these are going increasing by plus 20, plus 20, plus 20. So they're consistent. That means if these are consistent, then it's linear. So here, let's see. Let me just do 1. 20. This is where Desmos is way better, because you can just put this in a table and Desmos will draw a line through it for you. And look that up, by the way. It's called having Desmos interpreting the data. Okay, and then I'm just going to subtract the one before, 19.1482. And I'm going to discover that they're differences. You can do this with your thing as well, by the way. And I'm going to discover that the difference is 1.42. I'm not going to bother doing them all. You should do them all. And you should remember what forced... and this is why doing it once in a table is way better. Just let Desmos do it for you over and over again. That way you only have to create a table. There we go. So I can see that it's the same thing. Now, I'm sure if I do them all, I'm going to discover that the first differences between each of these is the same thing over and over again. And you might be tempted to say, therefore we have a line that's increasing by this amount. But you got to remember it's increasing by this amount per 20 degrees. So when you divide that by 20, so when I divide that by 20, it's actually increasing by this amount. So I'll copy that. It's actually increasing by this amount for every 1 degree Celsius. And that is because it is increasing this amount here for every 20 degrees Celsius. So to figure out how much it's increasing, oh god damn it, to figure out how much it's increasing per 1 degree, you have to just divide that first difference you found by 20. But let's read the question. Calculate the first differences and show that T and V are related to a linear relation. Yeah, when I did first differences, if the first differences are all the same, we're talking about a line. If it had come out no, and the second differences, the differences of the differences, were equal, it's a parabola. And if you come out with third differences, it's cubed. And that's how you determine from data what graph best fits the data. Find the linear equation of v and t in terms of t. That's a great one. So I'm going to say, let's see if I can I just shrink this? I don't want to get rid of it in case I'm supposed to come up with the data again. Ow. God damn it. I'm going to just try shrinking it. Maybe it'll work, maybe it won't. Not really. Anyway, we know that volume based on temperature, which I guess we're just going to call T, is going to be equal to mx plus b. And we can see based on my calculation that for each unit of x, it's going to increase by 0.08213. And you'd be very tempted to put this as the slope. But slope is based on 1 unit of x. And this is based on 20 units of x. So you have to divide by 20 to get that. And that's the trick. Now we just need to figure out a b. Well, we can figure out any b by looking at where x is, 0, and there's our b right there. Fortunately, they gave it to us. Had they not given it to us, you can plug in minus 40 for your x value here, and this matching y value here, and you can figure out b like that. But fortunately, they gave you, when x is 0, you're always going to see your b. So that's the equation based on temperature. Oh, and I've got to have the x is actually not x, it is volume, v. Oh, sorry, t. So it's 0.0821 times t plus this b. Solve t in terms of v for the equation in part b. Solve t in terms of v for the equation in part b. So now, if I guess they're asking us, I'm going to get rid of this data. If I need it later, I'm going to curse. I guess they're asking us to write now an equation based on t, and that means we unravel it. So t, so this, oh God almighty, is going to be equal. Yeah, I better not do it on that side because I'll confuse you. Keep it on this side. It's going to be equal to volume minus this, because I'm going to move it to the other side, minus that. So I might as well put it over here now, just so you can see. And then I'm going to divide both sides by 0. Actually, I'm going to multiply by the reciprocal. So I can see that volume is going to have this rate of change. And this, I'd have to figure out what this number is. So you take this number, divide by that, and you're going to have a new b that's like multiply. It's going to be like 2243 or something. Show that as the limit, as volume approaches for the limit t, it's approximately absolute 0. Well, I guess I need the equation now. Okay. So I'm going to take t based on v is equal to 1 over 0.0821 v minus, and now I'm going to have to take 22.4334, and I'm going to have to divide it by 0.0821 to see my new b. And there it is. And, well, I guess I could round up somewhere. There it is. So we can see when volume is 0, when it approaches 0, this becomes 0. And that's my new temperature of volume, which essentially means that that's absolute 0. Apparently, temperatures can't get colder than that. So I guess the point is that once your volume reaches a certain amount, it can't get any colder because you can't get a smaller volume. Interesting stuff. I never knew how that's how they. I hope that's how they came up with absolute 0. I'm sure I knew it a long time ago. I hate forgetting things. I don't know if anyone else hates forgetting things. I don't know if any of you have experienced forgetting things yet, but you will. Show using the properties of limits that this approaches 3, then this limit, that if limit of f of x equals 3, then the limit, of this whole thing divided by f of x equals 7. So they're saying that if this f of x is equal to 3, prove that this approaches 7. Interesting. As x approaches 5. Yeah, but x approaches 5 for both of them, which means f of 5 is supposed to be 3. And since I have f of 5 here, I can just replace it with 3. Don't quite know if and I can put a 5 up here. Don't know if that's quite the point. So I get 25 here, minus 4. Yeah, it looks like that is the point. So I get 21 divided by 3, which is 7. So how did I figure that out? Okay, let me do it in a bit more straightforward terms. They're saying, here's the assumption, this is true, that when this approaches 5, f of x is equal to 3. Well, where would I put the 5? They're essentially telling me that when f of 5, the result will be 3. Then over here, they're saying, make your x approach 5 again. Well, where do I see x? Up here. So I get x squared. Where do I see x down here? F of 5. The only question is, can I replace f of 5 with anything? Yeah, back here they told me f of 5 is 3. So I can just replace that with 3. Which just means 5 squared minus 4 divided by 3 is going to equal 7. That's all they mean by that. Essentially just doing super simple substitution, but you got to show by your work that you understand it. They're doing it again here. They're saying that if this result, so essentially they're saying if f of 4, because they gave us 4 down here, is equal to 3, use the properties again to calculate this. So again, they're saying as x approaches 4 again. So all you do before you replace your f of whatever, wherever you see x, you replace it with 4. And you say, do I see f of x there? Yes, I do. So I get to replace it with the value you told me it reaches, which is 3. Okay, 3 to the square is 27. So the answer to this one is 27. Really goofy way of doing it, except that they're going to have multiple x's in there. You essentially start on the premise that they give you f of 4 when they say that f of 4 is equal to 3. But before you can replace it, you should replace all your terms. So I'm going to replace this with f of 3. And I might as well have a nice f of 3 somewhere that I can just do it over and over. And I'm going to replace that with f of 3, but also be aware you're going to replace your x, not with 3, but with the value it's reaching. Now you just have to replace your f of 3 with the value they gave us. When f of 4 rather, not f of 3. These should have all been 4s. Okay, but f of 4 is equivalent to 3. So I can replace that with 3 and that with 3. So up here I get 9 minus 16, which is minus 5. And down here I get 3 plus 4, which is 7. Therefore, it's approaching this. This whole thing's approaching this. And the only reason you can't solve it, because they have an f and x formula in here that you have to replace with something that they give you. You can only solve these x's when they tell you this much. You can only solve this when they tell you this over here. The rest are just exactly like that. You don't need me to do that 3 times. Oof, I don't know if I can do some of these in part C. If I'm not prepared for it, I'm not going to do it because it'll spend hours to reach a wrong conclusion. So they're saying right away, they're telling us that f of 0 divided by 0 is equal to 1. Obviously, we won't be able to solve it. And prove that the limit of g of 0 as approaches 0 exists and is a non-zero. Okay. Oh, they're saying this is that. It's not 0. Evaluate each limit. Oh, and then they give us the limits. Oh, I'm sorry. I forgot to enlarge these. Same thing, I think. So up here, they're saying, so I'm going to just take this one. They're saying when f of 0 here is divided by 0. Now, remember, it's a limit, so it's not solved. It's going to be equal to 1. which is relevant. Is it relevant? Show me what the limit here is. Okay, good question. Well, if they're okay, here's a good point. If they're both going to be the same item, they're going to be dissolved. They're going to be reaching 1. So technically, since this is approaching 0 and this is approaching 0, let's say it's 0.0001, the only way these can match if they are approaching the same thing. So if this whole thing results in 1, they're going to be the same thing divided by each other. So you could say f of x is equal to x. That's about all you could say on that. Because if they're dividing each other, the only way you can achieve a 1 is if they're the same. Since they're both approaching 0, you can only say that f of x is equal to x. I believe that's the twisted answer. Then they're saying, since we just showed that f of x is equal to x, we can replace f of x with x. And g of x, they've told us, is a non-zero and exists. So let's call it 1. So this one approaches 0. I hope those are the answers. Otherwise, I just blew it. But the whole key here is, for these to approach 1, they have to be equal, I believe is the point. I hope it is. I always hated limits, and I actually think it's useless in calculus. I mean, I shouldn't say that, because I'm probably hurting someone's dreams. All right. If they're giving us this again, and this again, and then they're asking us to evaluate it. Oof, these are tough. I hope if these won't work unless my conclusions last time were accurate. So again, from this, I believe we're saying that it is equal to x. I hope so. Then they're saying the results here, as x approaches 0, is 2. That's a good question then. How can I evaluate it? That's a good question. I guess I could rewrite this in terms of f of x. Well, f of x, they're also telling me that as g of x approaches 0, what do I know? Oof. I'm not sure about this one. My brain just froze. I guess g of x has to be twice as much as x, is what you can say, generally speaking. It's going to be twice as much as x. And because they're equal here, when you take these, you're going to approach a half. That might be the answer. Simply because g of x over x is twice as much. I hope. I don't know if that's an accurate way to look at it. And then therefore, what is g of x as x approaches 0? If it's divided by that. Good question. It's not 0. This one's got me stumped. Well, we know that x, as it approaches 0, matches f of x. So you could rewrite it like that. I guess you could say it equals f of x, or 2f of x. I'm not sure. I'd have to look those up, and I'd hate to just lead you. Those are my guesstimates. Ask your professor about stuff that I can't solve. Evaluate. Okay, well, let's make sure we can't just put 0 in here. We get square root of 4 minus square root of 4. So, yeah, we can't. Why are they asking me to do that? We're just going to evaluate by multiplying by the conjugate. Maybe there's a trick. Okay, when I evaluate the top, just leave, oh, maybe the trick. No, it'll still work. So when I evaluate the top, I'm left with x plus 1 minus 2x minus 1. Why is it minus 2x minus 1? Because you have to treat that as a bracket, and the minus will affect both. Okay, so up top I'm left with minus x. That's all I'm left with. That's probably the key right there. And at the bottom, interesting one. Maybe I have to multiply by the conjugate at the bottom. X plus 1. Minus 2x, so minus x minus 1. I am definitely left with that at the top. Do I have any conjugates down here? No, I don't have any conjugates down here. So nothing will happen to the bottom, and I still will have the problem here. Okay, let's try conjugating, multiplying by the conjugate of the denominator instead. So we're going to multiply both by that over that as a plus. Let's see if that helps. So the bottom, I'm just going to do the denominator first, is going to become 3x plus 4 minus 2x plus 4. So the bottom is going to become x, just x again. And we still have the problem. Whew. I guess we can do from left and right, but I'm sure there's a way to solve this. I'm sure there's a way to solve it. Yeah, and the problem is down below we're left with x still. Whether we multiply by both, we're left with the same problem. Good question. Well, let's approach from the left and see. I don't know if this is the right course either, so here's 0. Let's try minus 1 in there. Minus 1 is 0 there. Minus 2 plus 1 is going to be a minus 1 there. So, so it can't exist. Minus 1 plus 1. Minus 2 plus 1 is minus 2. Can't exist. So we got a problem here. This whole thing can't exist at minus 1. Okay, that's a good point. Let's see what values there we go. So up here to stay positive, x can't be smaller. X must be bigger or equal to a half. Down here, x must be bigger or equal to 4/3. No, 3/4. No, 4/3. Negative 4/3. Over here, x must be bigger or equal to negative 4 seconds. And up here x must be bigger or equal to 1. So that's a lot of restrictions. Which one's the smallest one? That one. So that means our graph can only exist over here. So there is no limit, I think. I hope. Otherwise I look like an idiot. Because there's a whole bunch of situations in here that can't achieve a negative value. They can't be solved. Imagine you could create a fictional one, and I don't think so. But the lowest value is this one. For this one. Oh no, bigger than negative 1. Okay, so bigger than a half. Yeah, right there, bigger than a half. Maybe a negative half. Negative half. Bigger than a negative half. Oh, so they exist. So you got a negative 1, must be bigger than negative 1, must be bigger than negative a half, must be bigger than negative 4/3. Okay, they exist. I just got to take them really close. So I got to get closer than negative a half. Fair enough. So let's just take, I don't know, what's less between a half, a quarter? That's annoying. So negative a quarter. Let's make x equal a negative. Let's do negative 0.01, see if that helps. So I get square root of 0.99. Roughly square root of 0.99, again 0.98 or something. Divided by, what's 3 times? I don't know if this is going to help me. Divided by, what's negative 3.3? Square root of roughly 3.9. I'm going to get these close to 3.989. I don't know. I would punch that into Desmos and look at it. So assuming I could take accurate charts, maybe I should just do that. Unless my computer's slow. F of x. This is the nice thing about square. Let's do like that. Square root of x plus 1 minus. I'm going to put it all in big brackets so that I can divide it by something. Minus open bracket square root of 2x plus 1. All of it divided by, open brackets twice, square root of 3x plus 4, minus, open bracket square root of 2x plus 4. There we go. And there's our answer. So it's going to be undefined at 0, but it's approaching minus 2. I suppose if I plugged it in, yeah, I guess I could have just plugged in. That's pretty stupid of me. Could have just plugged in a really small value of 0. Let's say 0.1. And realize that I'm dealing with the square root of 0.01 minus the square root of, 1.02 over the square root of, almost 4 minus 4. Oh, that wouldn't have helped me at all. Square root, this would end up with 0.001. And up here, I'd be left with something in 0.1. It wouldn't be enough. I'd have to do the calculations like this. F of 0.001 up here. And then I'd see it's approaching 2, negative 2. But to do this actual calculation in the thing, left and right, what a pain in the ass. And I don't know if it's... punch that into Symbol Lab. See what it says. See how it solves it. Because I bet you Symbol Lab will do it. So far, 0 for 4 for me. And this last one, does it exist? Wow. Okay, well these will just... Oh no, they won't cancel out. And again, let's just see if Desmos will do it. Just because I don't... It always helps when you're learning, because you might think, well, it's cheating. But no, in the test it would be cheating. But for homework, if you can't do something, it's very smart to put it into Desmos once you can't do it. All right. Let's see if I got it right. I think I got it right. Oh. Okay. Let's see. Do you exist anywhere? Yeah, you do. Oh, yeah, you do. But does the limit exist? What limit were they looking for? As it approaches 1. Yeah, there's 1. So this is a good one where you would take it from the left and take it from the right and discover they're not approaching the same numbers at all. And same with the last one. You go from the left and the right. That's what they're trying to teach you to do. Sorry for wasting your time there at the end. I'm going to try to leave a note in the video saying just to speed past the last part. Hope the other stuff helped though.